Hi, today I want to talk about making better voltage management. Many people think that the most important part here is that you need a very good multimeter to measure the right way. But there are also things you should not do even with a very expensive multimeter, because that will give you false readings. So up to the video. So this is the circuit that we're gonna use as an example. It has to do with the high impedance or high resistance of the source which you want to measure, and the mistakes you can make that way. I made 5 resistors in series. They are 1 mega ohm a piece. These are more or less the measured values. The voltage is coming from a VREF at the 10.434 volts at a certain temperature, because if we're going to measure correctly, we should look at everything, so that is giving your instruments enough time to warm up, and making connections long enough so they can equalize in temperature and stop making C-back voltages, some for maybe another video. I've set 10 volts in it, and the current that's running is almost 2 microamp through 5 mega ohms. And now we want to measure the voltages there. A real life example for something like this will be in an oscilloscope, a non-analog oscilloscope, the high voltage divider from the cathode voltage, where you set the focus and the intensity and so. And in tube equipment you also have very high voltages, of high resistances with voltage, and there is something to consider when you measure in those things. That is looking at the schematic for the multimeter that is advised by the guy who wrote the service documentation, because you will see in a moment what the influence is if you use an analog meter or a digital meter, and what is causing these mistakes. This is a rather high impedance, but that is to make it very good visible. The smaller the resistance will be, the smaller the fault will be, and it depends on everything if it's important for you or not, but let me tell you what to look for. So this high-tech piece of engineering I made is the thing we're going to use today. These are the 5 resistors. There is a multimeter hanging over them at the moment, so they're hanging over a very high impedance, but that is not really the case, because it is parallel to the source and the source has a low impedance. So it is no problem to measure the output of the voltage of the VREF. You see 4 connectors here, but that is because one of them is measuring the current, so you can show what is happening, and that will be done by that meter there. You see there is almost 2 microamps, and if you want to know the voltage, then we can look up here, and there you see it's 10.4326. Yeah, and a lot of numbers is the voltage, and this is the voltage measured over the source but outside of the current meter, because that has a burden voltage, like I told in some earlier videos. You can see that if I remove the thing from the circuit, and now I'm only measuring the output of the VRF, and then we have a slightly different voltage, and that is the voltage we lose over the shunt of the current meter. Not very important in this case, but just that you know. So the first thing we are gonna do is put the video there, the recorder there. That is, we're gonna measure point 1, and I'm going to use a very normal standard multimeter for that, and it will be this fluke here. So you see I have the multimeter probes over the first resistor, the first 1M resistor, so we should measure very close to 2 volts there. But if you look at the display of the fluke, it's only measuring 1.74 volts. So is this fluke a very bad meter, or is it broken, or is there such a problem? And no, that is not the case. It is nothing more than you measuring the voltage with a 10 mega ohm impedance multimeter over 1 mega ohm resistor. And if you draw the substitution schematic of it, then you are putting 10 mega ohms over that 1 mega ohm, so lowering that 1 mega ohm resistance. You can see it also if you look at the current. The current is gone up to over the 1.99 microamps. The extra current you see here is the current that is used by the meter, that is running to the 10 mega ohm of the meter itself. If you look at my current measure video, you see that I use this meter to measure current by measuring the voltage over its own 10 mega ohm resistance. So you see that is a very big fault. If you want to adjust something like this and you measure over the 1 meg and you want to set the end voltage, then you are going to make a huge mistake. Because if I would adjust that until this meter gives 2 volts, then the total voltage will be much more as 10 volts. This is a rather big fault just over 1 M. But what if we measure it over 2 amps? Then you see instead of 4 volts we have already 420 millivolts volt. So it doesn't matter what kind of meter that you take in price or in accuracy. If this would be a 0.11111 ohm meter, it will still measure the wrong voltage. And if we look at the current again, we see it's now 2.135 microamps. So the microamps are going up, because in this case we measure of 2 resistors at the same time, and these 2 resistors together are 2 mega ohms, but we put 10 mega ohms parallel and it calculated for you. If we look at the board here, then you will see we have 2 mega ohms, the 2 in series. We have parallel the multimeter over, that is 10 ohm, but in this case I used the fluke. In reality it is 11 meg, if I remember well. And then you take the formula, and then the resistance, the total resistance the circuit sees is 1.7 M. So that is why the meter is showing the wrong values. So in this case we and if we go up to the range, we go like to here, we should have 6.16 volts there, and we are only measuring 5.37, and that goes up to the 7.34 instead of 9.35. And if we go all the way around, we are now measuring over the resistors parallel to the source, then we see it's again 10.2 volts. So the 2 is also a fault of the fluke. You see the measurement goes wrong every step up, but then when you're at the last step, the error is almost gone. At least that it looks like that is, because it's the 10 volt. But if you look at the current meter, it's now measuring almost 3 micro amps instead of 2. So that is, although the voltage here is not way off, the current in the circuit is way off. So things won't work the way they should work in this case. There's a possibility. It's not always the case, because there's still the same current running through that, but the power supply has to supply more, because current flows everywhere. But what if we take a modern meter with a very high impedance, like the Keithley, that is more than 10 gigaohm in the up to the 10 volt range. Some are like the Bryman here, and that is also a very high impedance, but only in the millivolts range. And we're working here in the 10 volt range. And there are not much meters that have that impedance at that voltage range, but the Keithley is a 6.5 digit meter. So now if we look at the Keithley, we can zoom in on it, because it's a long way there. Now we see we're measuring 2.13 volts. So if we look at our if I look at my paper where I have put the values, the measured values should be 2.1536 volts, and that was with the meter not warmed up very well at this moment. But more important, if we look to the current, we see the current measurement is still in the same ballpark. Without the meter it's 0.993 microamps. With the meter it's still the same current. There will be some extra current, but that is in the picoamps probably, because also through 10 gigaohms there is still flowing some current. But the voltage we should measure is the voltage we see. And then if we go to the second one, this is the second one here, then we should see 4 volts, and here we also see 4 volts. With everything cold it was 4.20 volts. It's now 4.019. And if we look at the current is still what it should be. There is no increase of current. And if we then look at the meter, because I told you that, but now you can see it for yourself. And then I will skip some and I go to the 8 volt tab. Then you see we're still at 8 volts. And if you will do the math and use the current measured, then you will see the numbers are correct. And like you see here, the current is still the same. So it does not matter. Here you see it's going one place up, but it is then we're talking 1 nanoamp, and it was already flipping now and then, so it's maybe 400 picoamps or so. And you see the meter is giving you the 10 volts over the 10.41 volts, and it is only something like 20 microvolts lower than the meter you saw before that, and that is the voltage we lose over the current shunt from the TTY that is measuring the current. I can measure the current with more resolution, but this one is nice and big to read. But then there are multimeters like this fluke like this Agilent. Make it a bit bigger, and there it is. And if we look at the Agilent and I do the same thing, that is a rather expensive hand multimeter, and it's with high precision. And but you see the problem. I'm measuring it. You see the current going up, and you see the voltage going down. So even that very expensive hand multimeter and modern hand multimeter compared to the Fluke so is making this mistake. This meter has a high impedance range, but then we have to go in the millivolts again, and this is too high for that. And just to make it complete, I'm not talking out of my, you know what, I will take the nice Bryman, and you see it's a bit shimmy. You see it's 1.8775. So also this meter is making a mess out of it. And in the millivolt range it is high impedance, but you cannot measure that. But what if we then use an analog meter like there were many moons ago, and there are still people who really like them. I like them just to play around because they're so pretty, but not to really use them. Now we have the I will first put it on the 10 amps, on the 10 volt range. The meter is also in the 10 volt range. These old meters are a bit how are you doing for all the types of connectors that I have. There's not really a standard in it. If we now take this one, so this is better. It's just going, it is just going over the 10 volts because it's 10 point something, and the meter is not really well calibrated. If I, sorry, I was in the wrong thing. It's 10 volts, so it is a little bit less than 10 volts, so it's better as I thought that it was. But now we going to measure the 2 volt position, and if we look at the meter, then this is not really 2 volts, because for the 2 volts he must be at that place. So we can go back one position to the 2.5 volt, and in the 2.5 volt we use the upper scale. And then it's still thinking that it's only measuring a few millivolts or so, because I'm very bad at reading those scales. And so this is 500 millivolts, and then we have here, so that is something over 200 millivolts that it's reading. That is not really a lot, but then if we look at the current that it's drawing, it's 2.643. So that's a lot of more current. But what if I clip it over the total thing and we put it in the 10 volt range again? Now you see it's drawing 51 microamps. So that is, we had 2 microamps, that's 25 times more. So an analog meter is completely unusable for measuring high impedance sources. So if you're in an old tube amplifier, now you see it's 3 microamps, and we added the 4 volt points, and it's still running something like 300 millivolts. That's not very good. They're very good in measuring current, by the way. If we now take an old tube amplifier, something like that, and there is some voltage written on a voltage divider like here, and they're saying that you have to measure 200 millivolts, and you use a modern multimeter, then instead of the 2 volts you measure 1.8 volt, or instead of the 200 millivolts in this case, you're measuring 1.8 volt. And if you take something like the Keithley, you're measuring 2 volts. And the 2 volts is correct, but the guy who drew the schematic and made the alignment procedure, he used an analog meter, and his meter was reading that value. So often in old tube amplifier or other tube instruments, in the list of instruments you should use, they mention an the voltmeters. If they talk about a vacuum tube voltmeter, then you can use a modern meter. If they talk about a normal analog meter, then you should use that analog meter or do the math, because you will never measure the values that are then drawn in the schematic. They won't make it as wild as in this case, because they designed the thing. They know that it is going wrong. So in that case, they say you should use the vacuum tube voltmeter, and that will give a reading that will be close to that of the Flux 77. So that is these are the things you have to look at when you're measuring high impedance sources, because you see the volts you will get, the readings will be way off. So I told you they are good in measuring small currents. This one has a 50 microamp input, and if you look at the meter, you see that it's just a tad under the 2 sign. It is 50 microamps scale. So we use the second scale that goes to 50. So you see that we here are at almost 2 microamps. So you see, if you want to measure microamps and you only have you don't have expensive meters with microampere ranges, you see that an old analog meter that you buy for a few bucks on eBay or so can do a great job in this. But for those who are interested, this is the inside of the VRF I was using. That's an LM399 like is used in the Keeley 2000 and in the Prema as a voltage reference. On the top you see a switching regulator first at the bottom to make everything between 5 and 15 volts enough to feed the 723 voltage regulator that is there to make the voltage for the VRF, and it is just made with 2 resistors, and there is a chopper op amp and a normal op amp there, so I'm not driving the output of the LM399 directly, and that goes to the terminals here so that you have a low impedance. There's a lot of filtering in there. You see a lot of things that were there, but that was only in the beginning while it was burning in, and I only left now those 2 resistors, and it gave me a little bit up over 10 volts, and it doesn't matter how much that it is as long as you know how much that it is. And I have several calibrators, but this is just I made a long time ago, and it's handy to use for things like this. It's safer to do it with something like this as to do it with a full-size calibrator. So I hope you learned something from this and you thought it was handy. So if you are happy with it, please give me a thumbs up. They say it helps, and otherwise I see you to the next video. Bye bye.